Hello, my name is Joanna Garcia. I'm a sophomore at Harmony Science Academy.
And my name is Manuel Gomez. I'm a junior at Harmony Science Academy.
And today our project is about standing waves.
Whether it's in Greece, and the philosophers observed that if they throw a pebble, it will create ripples throughout water, or many Spanish composers, when they would ever pick a string in their guitar, they all realized that all of this added a simple harmonic that which later came to be known as the wave.
When Hertz began conducting experiments at the University of Bonn, he was aware of the revolutionary work that was left behind by British scientist James Clerk Maxwell, who had produced a series of mathematical equations that predicted the existence of electromagnetic waves. This challenged experimentalists to produce and detect electromagnetic radiation using some form of electrical apparatus. Hertz took up that challenge and in 1887 confirmed Maxwell's theories about the existence of electromagnetic radiation. He proved that electricity can be transmitted in electromagnetic waves which travel at the speed of light and possess many other properties of light. So first off, a wave can be described as a disturbance that travels through a medium, like mechanic waves, or without a medium, like electromagnetic waves. The medium is the string. So a standing wave is a vibrational pattern that passes from one point to the other and is then reflected. That's what gives it its appearance. A standing wave is different from any other wave because instead of passing through an object, it is reflected. When the string is vibrated at specific frequencies, points along the string appear to be standing still. That's where it gets its name from.
Now, even though this is a standing wave, it nevertheless has certain characteristics that all waves have in common. For example, let's pretend that there's an imaginary line running through the middle of it. The points at which the wave line goes highest and lowest is its amplitude, or in other words, the energy that the wave carries. The higher and lower the distance, the more energy it has. Wavelengths is also a quantitative measurement. That means we can measure how long a wave is. The way we do this is usually, you see these two ovals right here? This right here is one wavelength. You see two ovals, but in reality it's just one upside down S going back to that rod and back to the other rod. But since it goes really fast, it creates the illusion as if it was two ovals. This right here is called 1 lambda, or basically the unit of the wave. So this wave right here is basically 2 lambdas. Now this is very important because lambdas are very helpful in determining the speed of a wave. The speed of a wave is usually measured in frequency. If I say that this wave has a frequency of 50, that means that basically the wavelength travels 50 times in 1 second. Wavelength is usually measured in hertz after the German scientist who discovered them, Heinrich Hertz. Now the reason why this is important is because knowing this allows us to understand a very important phenomenon known as resonance. Usually resonance is whenever you meet the frequency of an object when another object meets that frequency. That means that both objects have the same frequency. It's very similar to whenever an opera singer sings, and I'm pretty sure you've seen that the glass cracks. That is because her voice matches the frequency of the glass, and when they match the frequency, it creates resonance, so that's why the glass shatters. So as you can see, this string right here, it has a speed of 35.9 hertz. If I have a light source that matches the wavelength, the speed of the wavelength, then it will be seen as if the light is only one line. And this is because the time that the wavelength goes is the same time for the light source. So that way when the wavelength is going, the light source follows it at the same speed and you see only one line. However, if I increase the frequency of the light, it will create a nice illusion that the light starts to move. And if I keep increasing the power source of the light or the speed, it starts to move faster. And if I get to a point in which the frequency of the light is about 2 or 3 times the frequency of the string itself, you will be able to see more than one light. As you can see right here, you can see about 4 lights right here. And that is because even though the string is traveling at 35.9 hertz, the light is going about 4 times as fast, and that is why you can see 4 lights, because by the time the string travels once, the light will already have traveled 4 times. Thank you for watching.